Okay, thanks very much. So I'd like to talk about the future of physics, but I will start with the past of physics. This I've given earlier versions of this talk in which I led up to the big challenge of our age called the Anthropocene, which includes the problem of global warming, but also many other problems, all of which arise from the fact that now the biosphere is controlled to a very large extent by human activity, and we haven't accepted our responsibility for controlling the biosphere. That's, I think, what I would like physicists and everybody else to be thinking about. But unfortunately, right now, at least I am very distracted by a bunch of other things. For example, AI, and also the rapid decline of the United States that we're seeing under authoritarian rule. I really don't know the best ways for physicists to help out with these two problems. All I can suggest, I guess, is to be intelligent, critical, and courageous. I really hope you think about it. And I suspect that Brazil has a lot of lessons for the United States about how to deal with authoritarian rulers. The United States is very unprepared for this. But so physics is just one small part of what we should be doing in life. But for now, I'm decided just to talk about physics. So that's all I'll really talk about. So the 20th century was the century of fundamental physics, which it's hard to explain exactly what that means. It's a very interesting question, but I'll say it's the search for a very small set of universal laws that govern the whole physical world. So ideally, you could write on one piece of paper some equations, and then all the laws we know could be, at least in principle, though not in practice, derived from those equations. That was the dream. But progress in fundamental physics slowed down after 1980. And I think we can say by now that we're in a new era, but we still haven't fully absorbed this fact. Many physicists, especially theoretical physicists, still act as if we're in the old era where fundamental physics was the ultimate goal. So let me show you what happened. So I'll show you a timeline, and it'll be very focused on the standard model of particle physics and general relativity, because those are our two closest approximations to the fundamental laws of physics. The fact that we have two is part of the problem. So I'll show you in orange experimental discoveries that were later accounted for by theories. So these are brand new experiments. In green will be theoretical predictions that were later confirmed by experiment. Because I'm a theoretical physicist, if anything, I put that in green because that means the theoretical physicists are winning. In orange because the theoretical physicists have to be careful, have to pay attention. In black will be experiments that confirmed theoretical predictions. And in red are experimental discoveries that are still not accounted for by theories. So these are the open questions for theorists. I'll do it by 20-year periods, and I'd like to start at 1900, but I can't really, because in 1897, electrons were discovered, really the first fundamental particle to be discovered. And that was a big shock. Before then, people thought atoms were the smallest possible thing, and not even everybody believed in atoms at that time. Now, in 1905, Einstein predicted that light particles, he called them quanta, but later they were called photons. Also in 1905, Einstein gave a way to experimentally prove that matter is made of atoms and to actually figure out how many atoms there are in, say, a liter of water. So this was his calculation using Brownian motion to show how a small speck of dust will be randomly pushed around by atoms, and you can use that to figure out how big the atoms are. At that time, people didn't all believe in atoms. It's hard to believe, but it's true. Because they had no direct evidence until then. In 1905, space and time were unified, again by Einstein, in special relativity. So Einstein was clearly the hero of this early portion of the 20th century. Then in 1911, every atom was found to contain a much smaller particle at its center called the nucleus. In 1915, Einstein predicted that gravity is the bending of space and time. So first he unified space and time, then he came up with a theory of its geometry in which curvature in space and time causes gravity. In 1916, he used that theory to predict that if you shake a very heavy object, it will emit gravitational waves, gravitational radiation. And already in 1919, the bending of space-time by gravity was discovered as light bent around the sun. In the next 20 years, very different kind of things appeared. In 1922, the expansion of the universe was predicted using general relativity. In 1923, the photon was actually found. It took quite a while from its prediction to its experimental confirmation. In 1925, an amazing shock occurred, which I will summarize by saying that the universe is predicted to be governed by linear algebra. It's called quantum mechanics, but it says that vector spaces and linear operators rule the world. A complete transformation of physics. In 1926, the expansion of the universe was discovered by Hubble and others. In 1930, the first neutrino was predicted because it seems as if energy is not conserved in some nuclear reactions. And they predicted Pauli predicted the neutrino as a way to save the conservation of energy. In 1932, antimatter was discovered. In retrospect, Dirac's theory of the electron predicts that there's an anti-electron or positron, but he didn't believe his own prediction. So it had to be experimentally found that there's a particle that's positive with the same mass as an electron. And now we know that every particle has an antiparticle. This is a very quantum mechanical discovery. In 1932, the neutron was discovered, a neutral particle in the nucleus. In 1933, the very first evidence for dark matter was discovered. People estimated how fast our galaxy turns around and estimated the mass of the galaxy and discovered that the galaxy was turning around too fast to be accounted for by the gravity produced by the visible matter. That's a question that still puzzles us. Then in 1937, a complete shock, a partner of the electron was discovered that's about 207 times heavier, called the muon. So now we call these particles leptons, along with the neutrinos. And so this is the second heavy lepton. Again, nobody had any reason to expect that, and we still don't know why it exists in any deep way anyway. Then things slowed down a bit during World War II in terms of the number of discoveries. However, in 1948, a huge progress was made when special relativity, electrodynamics, and quantum mechanics were all unified into a single theory called quantum electrodynamics, or QED for short. This is the pattern for how we now understand particles and forces using quantum mechanics while taking special relativity into account. Then in 1956, the first neutrino was actually experimentally found. And also in 1956, something really shocking was found. It's called the violation of P symmetry, but what it means is that there's a fundamental difference in nature between right and left. You can do experiments to tell the difference between right and left. In other words, it's not an arbitrary convention. You could talk to a space alien 1,000 light years away and tell them an experiment to do that they could use to decide what you mean by the left or right. Then in 1960 to 1980, there was a huge burst of work on particle physics. This was the age of particle physics, you could say. The second neutrino was discovered, which somehow mysteriously goes along with the muon. Then in 1963, Gell-Mann came up with a theory of the strong nuclear force, predicting that there are 3 different kinds of quarks. That turns out not to be quite right, but there are 3, at least 3. There turn out to be more than 3 quarks. In 1964, it was discovered that CP symmetry is also violated, meaning that if you reflect left and right, and you also switch matter and antimatter, that the world looks different. So matter is slightly different than antimatter, and left is slightly different than right, but even if you switch both those things at once, the world would look a little bit different. In 1968, a beautiful theory was developed unifying electromagnetism and the so-called weak nuclear force, which is, for example, the force that lets neutrons decay into protons, electrons, and antineutrinos. And this theory predicted some new particles, the W and Z particle carrying the weak force, and the Higgs boson, which gives mass to the W, the Z, and we now believe all fundamental particles. In 1970, they predicted a 4th quark because they discovered that 3 quarks would lead to an inconsistent theory. And in 1973, for similar reasons, another pair of quarks were predicted, bringing the total up to 6, which is what we believe now. In 1973, a better theory of the strong force was invented, which actually has particles that carry the strong force, called gluons. So quarks interact with the gluons and thus stick together to form particles like protons and neutrons. In 1974 and 1977, the 4th entry discovered. Then in 1975, a 3rd heavy lepton was discovered, the tau. So we now know that we believe that there are 3 heavy leptons and 3 neutrinos, so a total of 6 leptons, and there are a total of 6 quarks. So there is a very interesting symmetry between the leptons and the quarks, just in terms of some patterns they obey. No, I shouldn't say a symmetry, I should say a similarity, which we don't fully understand, but seems to be important. In 1979, these gluons were actually proved to exist. Then, starting in 1980, things slowed down rather suddenly in retrospect. Discoveries were still made, but they are all either discoveries that we still don't understand yet, or discoveries that confirm theories we already had. There were no new theoretical developments at a fundamental level. So gravitational radiation was found. The W and Z bosons that carry the weak force were found in an enormous particle accelerator in Switzerland. In 1995, the 6 quark was found. So there are 3 pairs of quarks for a total of 6. Then some surprises. It was discovered that neutrinos can turn from one kind into another. So neutrinos leaving the sun are electron neutrinos, but they can turn into other kinds of neutrinos by the time they reach us. For example, we can also do those experiments on Earth now. In 1998, it was discovered that the universe is expanding faster and faster. People had thought that the mass in the universe would slow the expansion down, but there's some mysterious effect, sometimes called dark energy, which is just a name for we don't know what, basically, that says that some effect is making the universe expand faster and faster. Then from 2000 till now, there have been a couple of important experiments. The third neutrino was found, so that completes the 3 generations of leptons. And then in 2012, the Higgs boson was found, and that completes what we call the Standard Model, which is our current picture of fundamental particles and all the forces except gravity. So all the forces and particles except gravity are understood using quantum mechanics, using the Standard Model, and gravity remains mysterious because we don't know how it connects to quantum mechanics, and it's definitely not part of the Standard Model. The Standard Model lives in flat space-time. General relativity says that space-time is not really flat, it's curved. So there are definitely big challenges remaining in fundamental physics. What is the dark matter that's making galaxies rotate faster than we could explain and make the universe, make the galaxies clump up and form in the first place? Is it really a thing? Is there really dark matter? Or is there some flaw in our understanding of gravity, perhaps? Also, the universe, after a certain amount of time, seems to have started expanding faster and faster as it is now. We don't understand that either. Again, that could be connected to some lack of understanding of gravity, or it could be some kind of field that we call dark energy. We don't know for sure. There's some evidence that in the very early history of the universe expanded faster and faster, extremely rapidly. That's called inflation. But we're not really completely sure of that, and we certainly don't know what particle or forces made that happen. The Standard Model is an interesting theory. It's beautiful in some ways. It's complicated, but it's beautiful. But we don't even know if it's mathematically consistent. In fact, there's some evidence that it might not be. The Higgs boson has peculiar properties that might actually destabilize the vacuum in the Standard Model if our current understanding is correct. So we have a lot to do to understand the math of the Standard Model better, and also the physics. And finally, a huge challenge is reconciling the Standard Model and general relativity. They seem to live in separate universes, but obviously we have one universe. When I was growing up, I wanted to solve some of these challenges. I'm so old that not all these challenges existed when I was growing up, but definitely the problem of reconciling particle physics and gravity was an open problem, and I tried working on that. And I have to say that I didn't succeed, and I also have to say that no one else has succeeded. So things have been very slow since 1980. I got my PhD in 1986, and I've lived most of my career since then in this slow era of fundamental physics. And I don't know what kind of physics all of you want to do, but I think you have to understand that we are in a different era than the old days. I don't think it's likely that we're going to have rapid revolutions in physics, in fundamental physics right now, but there are other kinds of physics. So I have to say, don't be nostalgic. Don't read about Einstein and Bohr and think that you're going to be doing the same kind of cool stuff they did. You can do some new cool stuff, but it's going to be very different. All these attempts to combine gravity and quantum mechanics, like string theory, haven't worked very well. People have been working on them on string theory since the late 1980s. And I think if something isn't working well, it's good to try something new, especially if you're young. Maybe if you're old, you're too stuck in your ways to even try something new. But when you're young, you don't have that excuse. And I have to say that today there are more exciting things for you to do than fundamental physics. So although fundamental physics is really cool and it's definitely worth learning, I don't think it's actually a good thing to work on. Most branches of theoretical physics are doing very well because we have a lot left to do in using our knowledge so far of fundamental physics to study interesting things. So I want to tell you about a few interesting things that people are studying now. And the great thing about these is that we can study these using theory. So if you like mathematics and theoretical physics, these are great problems. But we can also study them experimentally, and often we can study them in fairly small laboratories, not enormous particle accelerators. The problem with things like quantum gravity and string theories, we can't do experiments at all. And we've learned, I think, that physics doesn't go very well without experiments. Sorry. So here's something. Excitons. So if you have a crystal and you knock one electron off of its atom, it leaves a hole, a place where there should be an electron, but it's not. So it's positively charged now. So the hole acts like a positively charged particle. And the electron, of course, is attracted to that. So the electron and the hole can orbit each other. The electron can move around, but also the hole can hop from atom to atom. So they can orbit each other, and they can form a particle, or a quasi-particle, a pretend particle, that's sort of like an atom, right? An atom has an electron orbiting a nucleus, but this thing is called an exciton, and it has an electron orbiting a hole. So you can make excitons in crystals by hitting them with a little bit of light or some kind of energy, say, for example, at low temperatures, and you can make these excitons and study them. So an exciton is a really cool thing because it's something orbiting nothing, a hole. Sorry. Got to go forwards, not backwards. So what can you do? Well, that's just the beginning of the story. You can do something cool like this. You can take a material that forms excitons, put it between two mirrors, and bounce light back and forth between those mirrors. Then, if you set up the conditions correctly, the photons can form quantum superpositions with the excitons. So you get a particle, a new kind of particle, that's a quantum superposition of an exciton and a photon. And these are called polaritons. So you can think of it as a blend of light and matter. These are particles that are a lot like light, but they actually have mass, unlike photons, which are massless. In fact, polaritons can form a fluid. They can form a liquid. It can be a superfluid, meaning a fluid with no viscosity, or it can form a normal fluid. And then superfluid will flow around an obstacle without any trouble. And that's what's happening in this left picture here. These are actually waves in the quantum phase of the polariton, photograph of those, believe it or not. In the middle, you see a polariton fluid flowing around an obstacle and creating vortices, so turbulence as it goes around the obstacle, like a normal fluid, like water flowing around a rock. Or you can make the fluid flow so fast that you get a sonic boom. The fluid is flowing faster than the speed of sound. So there is sound in polariton fluids. And here we have the polariton fluid flowing faster than the speed of sound. So this is really remarkable. We're making a fluid out of particles that are a blend of light and a particle that's a blend of an electron and the absence of an electron. So we're stacking concepts on top of each other, making more and more complex systems using the laws of physics that we know, but discovering phenomena that are surprising and take a lot of work sometimes to understand. Here's another: artificial special relativity. So what's this thing? This is a graph. The X and Y coordinates are the momentum of electrons that are moving on a flat sheet of graphene. Graphene is a form of carbon that forms flat layers. So the electrons can have momentum in the X direction and the Y direction only as they move along this flat sheet. The energy will be a function of the momentum Px and Py. And so here we are graphing it. But this function is very complicated. You may be used to a rock where the energy is the energy is the momentum squared divided by 2 times the mass of the rock. A nice quadratic relation. But in this system, the energy function is very complicated. And in particular, there are often 2 different allowed energies for the same momentum. So certain points in this graph look like a cone, or look like the top and bottom of a cone. That's the kind of relationship between energy and momentum that we expect for a massless particle, like a photon, in special relativity, where you call this thing the light cone in energy momentum space. So what that means is that electrons are behaving like massless particles in special relativity. But the speed of these electrons is much slower than the actual speed of light. This is sort of fake special relativity, where there's a fake speed of light that applies only to these electrons. So whenever you have an energy-momentum relationship that looks something like energy squared is momentum in the x direction plus momentum in the y direction, each squared, and I'm leaving out all the constants. Whenever you get a relation that looks sort of like this, that's the equation of a cone, and this is called a Dirac cone. So whenever you have a Dirac cone, and you may need to change the coordinates to get the formula to look like this. So in some coordinates, right near this point here, the graph looks like this in some coordinates. But whenever you have that, you get physics that mimics massless particles in special relativity in a world where there are just 2 dimensions of space and 1 dimension of time. So graphene gives us access to this amazing world where the speed of light is much slower, and instead of light, it's actually electrons that are moving around at its own speed of light. This same phenomenon happens in 3-dimensional stuff too. There's some kinds of metals where electrons act like massless spin 1/2 particles. There's some called Dirac semimetals, such as sodium bismuthide. I had to look that up. I don't know these particular materials very well, but I wanted to prove to you that they're actually specific metals that do this. And then some of them act like what you call chiral massless spin 1/2 particles. A chiral particle can only spin in one way. It can either spin in the same direction as its momentum, or it can only spin opposite its momentum. So when you have massless particles, it's possible to have this built-in handedness. And we can get that too. And that was discovered by that idea goes back to the mathematical physicist Hermann Weyl. So those are called Weyl semimetals. So we can now study all these strange things in the laboratory and study them theoretically, which is very beautiful and fun. But we can do even stranger things than that. So I was just talking about a world with 2 space dimensions and 1 time dimension. But we can actually make artificial universes that have 2 time dimensions. How do you do that? Well, you make special materials. They have a fancy name, hyperbolic metamaterials, where light moves in waves like this. Now, this looks like the usual formula for how waves move when you have a particle with some momentum P and some energy E. And I'm leaving out constants like Planck's constant here. Whenever you have waves like this, you need to know what's the formula. That's the formula for energy as a function of momentum, and then you'll understand what kind of thing you've got. Now, normally, you might have something like energy squared is momentum in the x direction squared, plus momentum in the y direction squared, plus momentum in the z direction squared. This k should be a p. I don't know why I wrote it as k. But the big thing is that this one here has a minus sign in front of the momentum in that direction squared. That's very bizarre. That means that if you took this red term and popped it over to the left-hand side, you'd get basically the formula you would expect if you had 2 time dimensions and 2 space dimensions. Energy is connected to time. Momentum is connected to space. This weirdo momentum really wants to hop over here and act like another energy. And so you are actually studying physics of light in a 4-dimensional universe like ours, but one with 2 dimensions of space and 2 dimensions of time. So see, in such a universe, you'd get this equation working for the electromagnetic 4 potential. This formula should remind you of a formula you might have seen in electromagnetism, where J is the current, or the 4 current in 4 dimensions. A is the 4 potential. But if you've ever seen this in your class, you would have seen a minus sign here because time is different than the 3 space dimensions. But in these weird materials, you get a plus sign. And so now it's acting like 2 time and 2 space dimensions. Now, you can have a lot of fun thinking about how weird the universe would be if there were 2 different time dimensions. Right now, you can walk around a circle in space, but in this universe, you can also walk around a circle in time. And that's very weird to think about. So this equation, I'm going to say some more fancy mathematical stuff just in case there's some math-loving students there. I'm sorry, I don't really know you very well, so I don't know if you're going to love this or hate it, but some of you may love it, and the rest of you can just take a little break and fall asleep. So the ordinary Lorentz group, the symmetries of special relativity, is called SO31. It's the symmetries of a universe with 3 space dimensions and 1 time dimension. But in these hyperbolic metamaterials, the symmetry group changes to SO22 for 2 space and 2 time dimensions. And this group is actually more beautiful than the usual Lorentz group. For the real math whizzes there, it's because It's more closely connected to the group where you use the complex numbers instead of the real numbers. I could explain that if desired. This equation also has a neat symmetry where you switch the two space dimensions with the two time dimensions. Because if you have two space and two time dimensions, you can imagine switching which one you call space and which one you call time. So we can now study all these crazy things experimentally and mathematically, and that's a lot of fun. Here's another thing. This is very popular these days in condensed matter physics. It's called topological matter. So there are many versions of it. The simplest kind is called a topological insulator. So in three-dimensional space, you could have a chunk of material which is insulating on the inside, so electrons cannot move through it, but the surface conducts electricity, so electrons can move on the surface. But the really cool thing is that electrons on the surface have their spins forced to be at right angles, perpendicular to the momentum. So they can either move around like this green one with its spin pointing this way, or like, this picture is annoying me now. This blue arrow should be pointing the same way as the green arrow. Oh, like this one here. Nah, I don't like this. I guess all of these are actually the same kind of electron. If they're in every case, you need to rotate the momentum 90 degrees counterclockwise to get the spin. But there's another kind of electron you can have where you'd rotate it clockwise. I'll have to fix this picture that I got off the web. You can never trust people to draw these pictures well. So there are known examples of these, which turn out to be bismuth compounds, like bismuth antimonide. But in general, there are lots of possible kinds of topological matter. And these are materials that you can describe using a field theory that has a Hamiltonian density that when you integrate it over a manifold or surface that has no boundary, it only depends on the topology of that surface. But when the system does have a boundary, you get boundary terms in your integral, and those create special states that live on the edges. This turns out to lead to an amazing bunch of phenomena, like that people are busy trying to understand and hoping to use in quantum computers. But it's mainly, for me, a dream world of mathematical physics where you can do experiments and study these things. So the most famous example of topological matter is connected to something called the quantum Hall effect, where you have electrons moving on a 2D surface in a magnetic field. Then the electrons can form superpositions with magnetic flux flowing across the surface, and you get crazy kinds of things called solitons and anyons, and a whole bunch of interesting mathematical concepts show up in understanding these. I just wrote a few of them. And I should say that it's still not fully understood. It's still a mysterious subject. I've been studying this book, Quantum Hall Effects, recently. It's on my desk right now, and I'm enjoying it a lot. But I would warn you that unless you have a professor who's already working on the quantum Hall effect and gets you started on it, I might urge you to learn about the quantum Hall effect and all these wonderful ideas that are connected to it, but then try to apply these techniques to some other idea concepts, for example, some other forms of topological matter. Because right now, so many people are working on the quantum Hall effect that it's probably a bit hard to do something really new unless you're like a super expert. I think it's generally better to work on things that are new. I don't know if that's really good advice to give to people, but that's what I did. And it seemed to work for me. Here's another thing that's, I think, the most exciting of all. It's a very broad category. It's called active matter. Here you see a flock of birds. If you may have seen these large flocks flying around, if you live in a place where you haven't killed off all the birds, And they will move around in very interesting ways. And there's no leader to the flock. It's known that basically the flocks just, each bird follows the nearby birds approximately. But then some ways that that works makes the whole flock move around like an entity. In general, active matter means matter that's made out of many particles, which are actually agents that consume energy in order to move. And they may have free will, or they may follow some complicated patterns in their motion. So besides flocks of birds, people can make self-organizing polymers out of, well, either artificially or there are biological ones like microtubules in neurons. And people can make these days swarms of microscopic robots called nanobots and make other kinds of self-propelled particles, small particles that have motors in them essentially and can move around and interact with each other. What's exciting about this from a physics point of view is that it's a new form of statistical mechanics. So you use statistical mechanics when there are too many particles to want to study each individual one. You want to study them using probability theory. Ordinary statistical mechanics tends to very strongly assume conservation of energy. And very often, but not always, it assumes time reversal symmetry, that the future is the same as the past for these systems. But active matter violates conservation of energy and breaks time reversal symmetry. Now, what do I mean by that? Well, what I mean is that it doesn't really violate conservation of energy. The birds fly around, but you need to feed them or they'll lose energy. But when you're trying to model them as particles, their kinetic energy is not conserved, and you can't easily describe them by a particle in a potential either. So it's actually easier to model them as particles that follow some law that is not governed by conservation of energy. So you neglect the fact that you need to feed the birds and write down a simpler model that can describe the flock. So this is an important theme. See, we've spent centuries learning fundamental principles of physics, like conservation of energy, like time reversal symmetry, which I will admit is violated slightly by elementary particles, but seems to be very close to being true. We've learned these principles, and when you learn physics, you learn to use these principles as much as possible. Because even if your equations are too hard to solve, if you know some principles, they'll help you understand what's going on. But it's often important, we now see, to study systems approximately using equations that violate those fundamental principles. You've seen this before. If you ever studied very simple equations for a particle in friction, so it slows down, if you only think about the particle itself, energy is not conserved. If you understand that the energy is getting converted to random motion of atoms and thus heat, then you realize that fundamentally energy is conserved. However, you may not want to think about all those atoms wiggling around when you're just writing an equation down for how a rock slows down as it's sliding on your desk. So we may deliberately use a simpler set of equations that violates the fundamental principles. That's sort of dangerous because, after all, fundamentally the principles are true. But it's crucial because we may need it to understand in a simple way what we see. So this, I say, is what we're doing a lot of in physics now. So in fundamental physics, we find these powerful principles. And I think when you're first learning physics, it's really crucial to master all these principles, like Lagrangian mechanics, the principle that the universe is controlled by a Lagrangian, not at all obvious. but true. And Noether's theorem, which says that symmetries of a Lagrangian give conserved quantities and vice versa. So it's taken centuries for humans to understand these principles, and we should never forget them. But now we can create and study more and more physical systems that are being approximately described by new laws, not fundamental laws, but approximate laws. And this opens up thousands of new worlds to explore. I've tried to describe a few of these worlds, like worlds with more than one dimension of time, or worlds where the speed of light is very slow, and so on. But those are just a few, and there are many more. Sorry. So we have lots to do, lots left to do. We need to figure out how to reconcile these approximate laws that we're learning or inventing to describe these new systems to the fundamental laws. And the best thing is all these thousands of new worlds, they're not actually separate worlds. They're all part of the same world. So they all interact, they all have the possibility to interact with each other. And we need to understand them in a unified way. We need to understand how all these new laws fit together into a single big picture. So this will keep us busy for at least a couple centuries because it's a much bigger job than figuring out the fundamental laws of physics, because there are many more of these approximate laws. So I urge you to take a try at this, and I think you'll have a lot of fun if you work on these questions. Okay, so I'll stop here, and I'll be happy to answer as many questions as you want.
All right, thank you all. So Professor Baez, well, that's very nice. Thank you very, very much for the talk, John. Extremely
Thanks.
interesting stuff. We're going to open up to questions now. So please, if you have, sorry. Quem aqui sabe falar inglês e tem alguma pergunta? Ou o quê? Tá, ok. Que eu só vou começar com quem tem inglês primeiro, que é mais fácil. Mas quem tiver perguntas, levanta a mão e faça em português e a gente traduz para vocês, ok? Então você. Okay. So state your name and. Se você quiser perguntar, if you want to ask.
Someone will need to speak into the microphone if you want me to hear it, when you want me to hear it. Yeah.
Hello.
Hello.
Okay.
I hear it.
So my name is Mila, and I'm actually I have a bachelor's degree in biology. I'm here just for exposure. And you've
Okay.
mentioned a couple of times about symmetry, and that really made me think about how in biology we think that chiral molecules just happened to end up being left oriented or right oriented. And I'm curious if if physics is researching this and researching maybe a reason for this pattern in
Lack of symmetry,
our
yes.
at least in our the biology of our world.
Right. Yes, they are. I'm fascinated by that. I'm not an expert on that, but people do study it. So the one very possible theory is what's called spontaneous symmetry breaking, which is that it could have worked out the way it does, or it could have worked out in a mirror reflected way. And it's just chance that leads to one or the other. So for that to happen, it has to be true that it's difficult to have life with a mixture of, say, left-handed and right-handed proteins, that they work better if they all have the same handedness. And similarly, sugars should all have the same handedness. If that's true, then if you have originally a kind of mixture of left and right-handed proteins and sugars, as soon as life begins to start forming, it will prefer to use chemicals of one particular handedness, whichever happens to be around at the time. And then, and life that has proteins of one handedness will tend to create more proteins of the same handedness. And so that will just win. So that's like, so it's spontaneous symmetry breaking is a very important idea in physics. And you can imagine, for example, if you have a needle standing perfectly vertically, it will fall down in some direction, and you can't really say which it will fall down, and it breaks the symmetry, but it just happens. However, there are some physicists who think that the symmetry breaking was not spontaneous, because in fact, there are some asymmetries in the environment, namely due to polarization of light coming from the sun, and also even some people have studied the fundamental violation of left-right symmetry that happens in the weak force. So there are some people who have written papers about a physics explanation of why we have the particular handedness in our biomolecules that we do. I don't know if those papers are correct. So, but people definitely work on it, and it's definitely worth thinking about. It's also, there's beautiful research on how people are beginning to understand how the asymmetry of the biomolecules, including the DNA, actually winds up leading to the fact that, for example, most people are right-handed. So it turns out that we now understand the growth of some organisms starting from a single cell to a larger organism, and how the asymmetry of the original biomolecules leads to asymmetry at a macroscopic level of the organs. And that people really are understanding, and it's really amazing.
I actually, now that you said that, I remember that there's like a condition that people were born with all their organs, internal organs, inverted. That's super
Yeah, that's
interesting.
amazing.
Thank you very much.
I'm left-handed, but I don't think my organs are all inverted. I don't know. I've never checked.
Excellent question. All right, who else has a question? Quem mais tem uma pergunta? Tá, pode ser. Tá mais perto aí. Esse é inglês?
So I'm actually a mathematics student, so my question goes towards a more mathematically based question. So I'm very interested in category theory and its many applications on physics, and I wanted to know if you know some new exciting applications of category theory on physics.
Well, I guess the big question is how new they have to be to excite you. So I think the biggest area in which category theory is hitting physics right now is in the study of topological matter, topological insulators. So I would urge you to read Urs Schreiber's papers on the fractional quantum Hall effect. I was talking about this quantum Hall effect book, and that already brings in concepts from topology. But when you get deeper into those concepts, you need to start understanding algebraic topology at a level that really brings in a lot of category theory, including concepts like higher gauge theory, where you're using higher versions of groups, that is, groups that aren't just sets, but are categories or two categories or so on. So there's a lot of really cool stuff going on there.
Thank you very much.
Sure.
Alguma pergunta? Sobre algum tópico diverso? No? All right. Well, John, there's a... Okay.
Well, thanks for your talk.
So,
Hello. Um, I'm a physics student, and I'm on my last year, and
uh-huh.
I was always really interested in theoretical physics, and recently I've sort of gone away from that and started working in well, pretend to work in sort of biological applications in physics, and I don't know. I think at least here in Brazil, there's still really I don't know how it is in the U.S., but this sort of ethos, this philosophy that theoretical physics is the real stuff, right? It's the real. It's what's
Uh-huh.
what actually matters. It's what the real, the real smart people do. And I don't know.
When you say theoretical
This is
physics,
something that
when you say
I think a lot about. You know,
when you say theoretical
fundamental
physics, do
physics.
you mean particle physics and general relativity, that kind of stuff? Yeah.
Yeah,
Right.
yeah.
Yeah, those, I mean, theoretical physics includes a lot more, right? So there's condensed matter physics and so on. It still can be very theoretical and mathematical. You still need to be very smart to do it. But I understand what you're talking about. Um, so it's a problem, this attitude, and that's what my talk was in part about. But I didn't know. So what's your question?
I don't know. I wanted to talk about that in general. I don't know. I didn't
Yeah,
really have a question. It's
yeah.
just something that's on my mind a
Okay.
lot.
Yeah. Yep.
Sorry.
Yeah. Well, good. It's good to think about. We just have to break out of that attitude. I'd say that's a 20th century attitude. We have all these heroes like Einstein and Bohr and Schrödinger and Heisenberg and Dirac and so on and so on. They were discovering wonderful things in fundamental physics. But if you notice, if you pay attention, you see that starting in the 1980s, we get less and less of that. And instead, what we see are incredibly intelligent people like Hawking and Edward Witten, who are doing beautiful work, which, however, does not connect with experiments. There's no experimental predictions that they are able to make. And that's what's happened to fundamental physics right now. I'm not saying it will always be that way, but I think it will be that way for the foreseeable future. And so I think if you want to do physics that's really physics, meaning it connects to experiment, instead of mathematics, mathematics is great, okay? I'm a mathematician, but if you want to do real physics, I think you have to move away from fundamental physics towards things where people can do experiments. Biophysics is a huge and wonderful subject full of new concepts that we're just barely beginning to understand. We don't even have the language really for making biophysics into a really polished subject yet. And so if you want to work on a subject and do some really exciting work, you should not work on something that used to be exciting and is beautiful now. You should work on something that's a mess now, and you try to straighten it up, and then you will make the beautiful discoveries.
So I would like to ask a question about something you talk about of artificial special relativity, and that really piqued my interest. And so I want to ask about when you talk about we have two time dimensions and two spatial dimensions, how much of special and general relativity we can still use to study this new area you talk about?
Yeah, so for special relativity, you can take a lot of the equations of special relativity and in particular quantum field theory, which lives in the space-time of special relativity. You can take many of those equations and just change a plus sign to a minus sign to convert one dimension of space into one dimension of time. However, some things change dramatically. So it's, for example, we tend to expect that the light cone has two separate pieces touching at one point. But in the universe with two space and two time dimensions, it's not like that. It's connected. There's no one point that you can remove to disconnect it. So in other words, there's no invariant way to distinguish between the future and the past, because you can rotate time, you can rotate around in time and connect this direction of time all the way down to this direction of time. So that changes some things very dramatically. So it's a very beautiful mixture of things that stay the same and things that change.
John's Greg Egan has that novel Dicronauts, right? So in case, wait a minute. Caso vocês não saibam quem é o Greg Egan, ele é um escritor de ficção científica e um físico matemático também. Ele escreveu um livro onde ele propõe duas dimensões temporais e daí na página da internet do livro tem uma explicação de todo como mecânica quântica e relatividade funcionaria nesse universo. E daí funciona para so just explaining how Greg
Yes.
Egan. Yeah. Any question?
So, hello, can you hear me?
Hi. Yes.
So, thank you for the talk. So, I had this calculus professor, and he once questioned us about the difference between physics and maths. And I mean, he was thinking more about theoretical physics. And he argued that for him, he said that the difference was that physics is like math with boundary conditions. So, and I know I was thinking about it, and I don't know, I kind of disagree, but he presented good arguments. So I don't know, what do you think about?
What do you think he actually meant by that? What kind of boundary conditions are you talking about?
Oh, I don't know. For example,
Oh.
like when you apply the Laplace equation, so you could solve generally for I don't know, for any function like density of charge, an arbitrary density of charge, and not necessarily one that follows the nature way of group charge. I don't know. So it's like literally applying the maths with the things that nature gives to us. So I don't know. Did you understand?
Yeah, I think I understand. Yeah, I've never thought of it that way. I think a lot about the difference between math and physics, but I have some other bunch of ideas about that. um, I I often get asked from students whether they should go into mathematics or go into physics, and then I try to psychoanalyze them. I try to figure out what they're like to tell what they like. I think so. For me, a big difference is whether you enjoy arguments that are completely rigorous and like to prove theorems, versus whether you like to use intuition about matter, whether you like to think about things wiggling around and you're willing to be a little sloppy about your rigor, but because you are so happy that you're talking about things that are actually there. So I think of them as like different mental attitudes. And there are some great people like Edward Witten who can go either way. But I'd have to say ultimately he's a physicist. He won the Fields Medal for mathematics, but not by proving theorems, just by coming up with amazing mathematical ideas that other mathematicians converted into theorems. So he was using physics intuition to come up with those ideas that mathematicians hadn't discovered. But anyway, that's sort of different than what your professor was thinking about.
Just a minute.
So Hello, my name is Arthur. I'm a master's student. Um, my question is like it's connected to some of the other questions and the theoretical versus experimental physics wars, I guess. Um, during the presentation, it seemed like it's important to be like a little free mind while doing theory and whatnot. But there's a field like, and it's the name of this seminar series, like philosophy in physics, that it seems to be left out of this equation. And what is the importance of like philosophy in trying to connect this two areas and like solving this kind of uh, battle, I guess.
Sorry, which two areas? Connect.
Theoretical and experimental physics. Like,
Yeah,
what's the
okay.
role of
Yeah.
philosophy in that?
Yeah, so I th I think on the one hand, philosophy is potentially very important, but I almost always avoid talking about philosophy because to make any first, philosophy does not create solid answers that you can just tell somebody and then they know it and then it's done. Philosophy eliminates confusions and it opens new questions, but it only works when people are very careful in their thinking and slow and gentle. And so it can work very well in a conversation between two people who are trying to figure something out and who aren't trying to win an argument, but are just trying to understand things. And it can help you escape different ways of being mentally stuck in whatever problem you are in. But when you're done, at least for me, you don't actually need to say the philosophy when you're done. It helped you out. It can help you out in many ways, but not by producing a solid product. I mean, I've read philosophy books, but I've never at all wanted to write a book on philosophy because I know that anything I wrote, I would wind up disagreeing with a day later. So to me, philosophy is like going back to Socrates. I think it works best in conversation.
All right, before I move on, I have a personal question. You commented on the matter of the Anthropocene. Now, the people here are from the Brazilian Physics Institute, and a lot of the undergraduate students and there's a lot of them, that are working here and eventually will get a master's or, end up working for whatever else. Actually, a lot of the focus of our institutes are with ecology, regarding
Great.
biological matters. Specifically, our physics department is very concerned with medicinal purposes and such. So I'd like to ask you, using sort of what kind of excites you in these prospects of these new ideas in, condensed matter physics and emergent physics and the physics of complex phenomena that could be useful somehow to the crisis of the Anthropocene as we see it. Either the use of new materials or new ideas. What do you see?
I think, yeah, that's a tricky question. I'm very glad to hear that a bunch of people are working on ecological issues. I sometimes have given a talk where I'm trying to convince people to do that, but I see I don't need to convince you to do that. So good, a lot of you. I think condensed matter physics has important but somewhat limited applications to the Anthropocene. I think developing new batteries, more efficient electronics it's important. and condensed matter physics is important in that, but I don't think that's what's going to be the key to grappling with the Anthropocene. I think understanding human behavior and learning to work with actual real world humans is what we really need to do. And physicists are not the main experts on that, I must admit. I went into physics because I liked things that were easy to understand with equations, and people are apparently not so easy. But we really need to change human behavior to do well in the Anthropocene. So how do physicists do things like that? I think it's an open question. There's a lot of work on modeling. I'm doing a lot using category theory for modeling in epidemiology, and I really want to start using it with some economists. But the category theory doesn't solve the problems for you. It just makes it easier to work with the models. So I'd have to say that's a really tough challenge that I don't think anyone knows a great answer to. I'm sorry to be somewhat disappointing there, but we're in for some serious difficult times ahead with regard to the Anthropocene. And I'm afraid that my generation has left you youngsters to figure out what the hell you're going to do. So I would say start thinking about human behavior as the key.
Behavioral modeling and such.
Behavioral modeling is certainly important. What people, we all feel sort of trapped, right, in the world that, like, for example, I may feel I have to drive a car because I live in a city and I live out in the suburbs. I have to drive into the city. I could want to stop driving, but I can't because everyone else is driving. So humans organize into these patterns where everybody sort of does what they feel they have to do because everyone else is doing what they feel they have to do. And understanding how to change those systems is really important. And I think not at all obvious. I mean, one way it'll change is if there's a disaster, right? That's the old standard way. Is you wait till a problem becomes so terrible that there's like a catastrophe, boom, and things change. We would like to try to minimize the amount of deaths due to global warming, and that'll force us to develop ways of changing human behavior that are short of waiting for a catastrophe.
I'm going to try to personally continue that conversation later, but for now, another question.
Hi. Is it? Can you hear me?
Yes, hello. Yes.
Oh, I was about to talk about the same thing, the Anthropocene thing, because I also feel like the more I think about, the more time goes on in my life, I feels like it's not really. We're in a really terrible situation politically and climate change and everything, and it feels like the world is on fire sometimes, literally, and it's hard to motivate myself. I'm doing a PhD in pure math, and it sometimes feels like what I'm doing is completely useless, and it feels like it's not. It's either if I try to do modeling too, that's not the way. Like it's not the way that like we're not gonna solve this problem by institutionalized science and like modeling and stuff. Feels like there should be radical change in some way, and I guess my
Yes,
question.
I feel the exact same way. Yes.
Well, that's good to know. And
What's
I guess
you have a question? I mean, you don't need to have a question. It's already
I
very
guess
good for you to say that, but
that's how you feel like personally, because sometimes it feels like you're like an older person and there's like young people asking you stuff, and like if someone would ask me, I would say like, we should just leave the university and do something else and try to do something different.
I tried to do something more focused on climate change And I eventually realized, well, if human institutions were working well, then maybe I could do mathematics connected to climate change and that would get turned into something useful. But right now it seems that the governments are not really doing enough about climate change, and so it doesn't really work. Like you said, modeling might work if people would do things based on the models, but they don't seem to be doing that much. I mean, there are exceptions to be sure. So anyway, so I tried to take more direct action, and then I realized that I'm just not good enough at politics to do the things that are the most effective. I think that the real issues are political. And I went into mathematics sort of because I'm bad at politics. I like I like thinking about things that are very rational and beautiful and simple. And so now what I'm doing is a mixture of pure mathematics and applied mathematics connected to modeling and epidemiology, where I'm working with someone who led the Canadian response, the Canadian modeling of COVID, and is doing other public health issues and wants to use category theory to develop better software for epidemiology. And so what I do is I spend half of my time doing that modeling, or actually developing software for modeling. That makes me feel like maybe I'm doing something useful, but I also keep doing half of my time doing pure mathematics because I discovered that I need to do pure mathematics to keep from getting depressed or to keep happy, to stay happy. I just eventually realized that my ultimate reason for doing pure mathematics is that it's so beautiful, it calms me down. And so it's a sort of maybe a somewhat sad realization that you're doing some subject because it keeps you from going crazy. But what the heck? I mean, if that's true, that's true. So you might as well do it, you know. So I think mathematics is extremely beautiful and does have the potential to make people happy. And I think doing a certain amount of that is a very good thing.
Thank you. I think I do math for the same reason.
Okay. So I think it's good to just admit it. And maybe you want to do something else also, but maybe you don't want to, maybe it's not good to quit doing pure math if it really makes you happy.
Peraí, não sei quem.
Hi, thank you for the talk. I'd like to know your view on the segmentation of science and like the many branches we have. Like if you think in olden times, like the big guys that we know, they weren't only physicists or mathematicians or biologists, they were all of that. So, and I'd like your opinion if nowadays are we able to, is it possible for us to make science in a unified way, in a multidisciplinary way, even though we have so many specific branches? Thank you.
Yeah, I think that always well, not always, but it's very often that the most exciting developments happen at the border between two or more branches of science. The solid center of the branch is usually some body of theories and understanding that's been worked out fairly well. And that makes it very hard to do really original work in the center. Whereas when two subjects start to meet, there's usually room in the middle there where there's lots of stuff that isn't understood. And then you can do interesting things. And I think it's true even now that most of the people who are doing very exciting original work are at the borders of subjects. So the way the academia works, you almost are forced to concentrate in one subject in your education. And I think there's something good about that, because that means that at least there's one subject that you are supposed to know very well, which is better than not knowing anything very well. You want to be able to get fairly deep in one subject, I think, to have a certain kind of mental strength. But you'll see that a lot of people, when they then go on after their education and start doing original work, they switch towards, not switch, but they combine their knowledge with some other new work. And so I urge everybody to be open to combining biology with physics, combining physics with mathematics, combining biology with mathematics. I think that's where the fun is, and that's where the undiscovered mysteries are.
Question here?
Hello, Professor. Can you hear me?
Yes.
Okay,
Yes.
so I have a question regarding the connection with physics and our in E and our world. Like, how do you be ethical in our research? Because, like we are said, that sometimes the world feel like it's burning and everything is going horrible. So, how we can be ethical in our research, and how we can make things that will, like, at least for uh, the prospect, make uh, what we are living somewhat better. So thank you.
I guess a big question there is whether you're doing very theoretical work or whether you're doing work that leads rather rapidly to technologies. So when I'm doing theoretical work, one of the simple things I try to do is to not make things worse. So it's very typical in academia to do a lot of traveling if you're successful. So a successful scientist often gets invitations to fly around a lot and go to lots of conferences. And it almost sometimes seems necessary to be doing that. But that really has a lot of carbon emissions. And when I studied my carbon footprint, I discovered that by far the main contributor to my carbon footprint was travel. And so now I've cut back on travel a lot. I think it would be hard for me to do as a younger researcher, but now I basically avoid going to conferences unless they're fairly nearby. So that's a very interesting challenge there. I think everybody should be working more on trying to communicate electronically, like we're doing right now. So I'm very glad that you did not invite me to Brazil, even though I'd love to go to Brazil. I've never been to Brazil, but I'm very glad that instead of making me burn a couple of tons of carbon to see you, we're doing it on Zoom. I think we need to improve virtual reality a lot, because right now I can just barely see you folks in the back rows there. I can't have really personal conversations with each one of you. We need to invent technology that makes that a lot easier. So minimizing the damage, in other words, if you're doing theoretical research, try to do it in sane ways. When you're doing engineering or science that leads to technology, try to develop technology that at least its first use case is actually clearly good. So for example, there's a lot of money going into artificial intelligence. I'm very skeptical of artificial intelligence because it's mainly being used as a profit-making mechanism for very large corporations, including, say, Google, Facebook, and so on. And I don't think I want to be contributing to that. So although there are lots of people trying to hire category theorists, believe it or not, to help with AI. I've decided not to work on that. Not because AI is necessarily bad, but because the first uses of it are likely to have a lot of negative consequences that I don't want it to be my fault. So instead, I'm trying to use category theory to help epidemiological modeling. For example, models of type 2 diabetes or other diseases, because there it seems fairly likely that these models may actually do something good. I can't control the use of this category theory modeling technology. Someone could take this technology and use it to model other things that I don't want, but at least I can push a little bit in the direction of the things I like, and I think we can all try to do that. So you may get different job offers from different companies, and you have a little bit of a choice there in which direction you go and who you are helping out. And please try to push in the good direction, whatever you think is the good direction.
Question here?
Which always takes struggle, right? I mean, if you do the easiest thing, you're just going downhill, you're just like flowing along, going down the waterfall. That's very easy to do, but I think doing the right thing always takes some extra effort.
Hello? Yeah. Can you hear me? Yeah.
Yes.
Okay. Hi, John. Thank you very much for the talk. It's very interesting. I mean, you covered several topics, which are very interesting, I say. In fact, I must say I share most of your views on these topics, you see. But I don't want to ask a question, but make a comment because we are among young people here, and the message is being a bit depressed, you see. I think we should be a bit more optimistic, you see. First of all, I think the first attitude you should have is not try to save the world, because you fail and you'll be frustrated, you see. I think that's too big. You cannot end up trying helping saving the world in other ways. For instance, try to look at the topics that turn you up. If some topic turned you up, it's because well, first of all, you like it and you might be good on it. So try to work on what you like and you feel good on. Then you are going to give good contributions, you see. I think that's the first thing. That's what I tell my students. I mean, do what you like, because no, it's okay. Try to do what you like. If you do what you like, you'll be good on it and you'll be successful. Not necessarily, but you'll be. The other thing is about this thing. I mean, we are scientists, so that's why you should not try to save the world. Scientists are not made to save the world, even though many of them helped saving the world. But connecting with this relation between physics, mathematics, and biology, I think if you're a physicist and you want to help biologists, what you have to do is go to their lab, stay there, look at them, try to see what are their problems, you see, try to understand what is the problem they have, and see if you have some idea to help. But if you stay outside of the lab, trying to imagine what you can do for biology, you fail, you see.
Yes.
If you want to help mathematicians, if you are a physicist, go to the maths department, talk to mathematicians, stay there, have coffees, live a bit inside the department, trying to see the problems are. And then you may help them. But if staying outside and just trying to imagine what you can do, help them, you fail, you see.
Right.
So that's it.
I completely agree with this second point of yours. So the reason why I'm working on models on using category theory to help models of epidemiology is because I have a very good friend who's a computer scientist who works on models of epidemiology, and he has specific things he wants to do, and they're very sensible things, and he knows that category theory can help, and he knows how it can help, and he just needs a little help with that. And then it's very easy for me to get in there and start helping him out. If I had just said, okay, I'm a category theorist, I'm going to start trying to make up models of epidemiology, I would just make up a bunch of garbage. It wouldn't be it wouldn't be good at all. So and it's not just me and this friend of mine. We're working with two computer scientists who are experts in category theory. So working with a team of people with different knowledge, doing who know different aspects of a problem is really essential for this interdisciplinary work to succeed. And so, yes, I agree that you have to go talk to other people and find out what concrete problems are to have a chance to solve them.
Now, if you don't have any issue, you can, again, as I said, you can say or stay as much as you want. It's been 40 minutes over, so if you want to go off or if you want to continue, we can, you know.
I will probably have to quit in, let's say, 10 minutes. My wife will eventually be the one who gets tired of this, not me, my wife.
All right. So let's, okay, so we have 10 little minutes. Does anyone have any other questions or comments or addenda? Or, all right. Before, just a minute. A gente tinha falado, né? Qual era a outra questão que a gente tinha comentado, Marcos? Ah, entendi. All right. Well, all right. Oh, okay. Yeah, sure. Before the 10-minute little window, we want everyone to like take a picture with you, you know, so that's sort of, I don't know,
How does
just
that
fair.
work?
Oh, yeah. So everyone just come here to the front. And we would
Okay.
like, yeah, you can see there's a lot more people than we're used to as well. And everyone really liked your talk.
Thanks.
Yeah, and of course, and I find it's interesting. You are one of the most knowledgeable people I personally happen to know. And it's impressive to me how every single question you had something worthwhile to say. That's somewhat amazing compared to, you know, other professors and all. But anyways,
Well, a lot of what I said just common sense. But anyway, I'm glad it was helpful.
all right, let's. I'm just organizing everyone here. All right. Good Lord. Jesus, there's a lot more people than I thought. Bye. Oi? Yeah, so we're gonna take the picture with everyone, and
Okay, I hope
we're gonna
you
send
send
it
me
to
send me a copy sometime, because right now I just see a bunch of people's backs, right? So
it's you're together with us.
It's okay, but I'll see your front later, yeah.
Spiritually, we're here with you, you know?
Okay, great, great.
Yeah. All right. Yeah. It does. Okay, now on if what, peraí, just a minute. Quem quer sair, obviamente, pode sair. Eu tinha, quem era a garota que tinha uma pergunta? Mais um comentário? Ah, você é baixinho. Right, you can ask.
Hi again. So we've talked a lot today about many areas of science coming together. So I'm very passionate about that. I actually, it's more of a comment than anything else. So, I'm doing my master's right now in computer science, and I'm trying
Mhm.
to understand how interactions work, interaction prediction with weak label, imputation, and stuff like that. So I think that where I'm working right now, people are way less concerned about ethics. I think that the computer science area is more concerned about what they can sell and
Uh-huh. Yep.
in general more of a product than science in itself.
Right.
So I'm really happy that I came here, and a lot of people are also trying to make something more integrated.
Mhm.
Um, and I think it's also like a good opportunity to maybe these types of um, gatherings are important to maybe you start talking to people and you create little
Mhm.
pockets of communication and
Yes.
yeah, I'm just really glad I came. Thank you very much.
Sure, great. Well, that's a good comment. Yeah, sometimes it can be that lots of people are not talking enough and they're all suffering a little bit because they worrying about things and they don't think anyone else cares. But then if you just meet and start talking, then all of a sudden it's already starts feeling a little bit better. Even if you haven't solved the problem, at least you know that there are other people trying to solve it. So yes, computer science can easily become, it's so practical, it can easily become just a tool for large corporations and uh, but I think it but there's still room to have to do things that are different than that. So I hope you can find your way towards doing something you like.
Yeah, I was in a lab that I am still keeping touch with them, and I gathered like a little workshop for them about the things that I've learned here so far. And
Hmm.
I tried to introduce my lecture with like the good points and the bad points about AI, and actually I couldn't think of a lot of good things. I know that my research as well being used for um, disease prediction, but
Uh-huh.
it's I have a limited idea of what else good can be done with it.
Well, I think all sorts of classification and other scientific tools have a lot of potential for good. But right now, it seems that companies want to stuff large language models into every single piece of software that we interact with. I just got an update on my Android cell phone. Now I have to figure out how to turn off all the AI because I don't really want a phone that's talking to me. But they've decided that that's what we need or what we can pay for. So yeah, I can understand some pessimism about AI, but it's mainly the large language models that are driving me crazy right now.
Yeah, I think it's it's kind of our job now to figure out good things to do with it.
Yep, yep.
Well, Professor Bays, so 2 minutes left of your 10 minutes. So I guess we're closing now. I, of course, want to thank you for being here.
Thanks.
It's an extreme pleasure of mine. Sorry for all the late emails. I am a little bit of
Uh,
an airhead, but well, thank you, and thank you all
yeah,
for all
great.
coming here.
Yeah, it's
And I
great talking to a bunch of people. Yeah.
exactly, and well, whenever you want to make another talk again, we're happy to, whatever rant if you want to do like a rant for 2 hours, we're open to it. So.
That would be more exciting. Yeah, if you told me, go ahead and rant, then I could really get going. Yeah, okay.
All right.
Okay,
Well, thank you, Professor Bays.
okay, okay,
And
thanks very much. Thanks to all of you. Yes. I
goodbye.
will, bye. I'll take off now. Bye.